Well, good afternoon. Welcome back to your second lecture of Chemistry 401. One or two announcements. First off, I did post the video of last time's lecture, and it is on the Chem 401 website. There is an issue with it, though, and that is that it is not truly accessible because the closed captioning at the bottom is not complete. And so there is an issue with me linking to it from my Chem 401 website, which means if you want to have access to the lectures, get access within the next few days, bookmark it, whatever, but I'm going to take the link off my Chem 401 website, but I will still post the lectures. And if accessibility in any part of this class is an issue, please talk to me directly, because I take it seriously, and I'm working on it. Let's say that, right? And if you want to talk about any accessibility issues, any DSPS issues, and any issues at all, it is my goal to be there and do as much as I can to help you get success in this class. Any questions before we begin? Okay. Well, where were we? We were doing kinetics, and what we talked about was reaction rates, how to get a reaction rate that was not dependent on the coefficients or whether it's a reactant or a product. Reaction rate is always positive, okay? And we solved our first initial rates problem, and we used data based on initial rates because initially the rate is only the rate of the forward reaction, and there's no reverse reaction possible. And we'll talk about all that in discussion this week. Now, to continue with this problem, did opening that door change the amount of glare? Is there anybody who can't see? Would you prefer to have the lights on or off? I tried to turn some of them off, and I couldn't. Let me see. How about that? That's getting worse. Okay. So, so not right now, but if you have any feedback on my lecture style, that's changed. Good. And I am videotaping. I have to check. Please let me know that as well, because it's a work in progress, as you know. All right. So for this particular problem, we're going to work this one. Then there'll be a companion problem on the next page. Companion problems after some initial issues, the answers to which have been posted for this chapter already. So for this particular one, using ratios of logs, well, it says for this reaction at a specific temperature, from the following data determine the rate law and rate constant. Do it the long way with the ratio of logs. Well, I'm going to change that a little bit. Do it anyway. And that's two words. Anyway. Not do it anyways. That would be what you have to do anyways. And I say that because there's two ways to do these types of problems. There's the way that I showed you last time, which involves ratios of logarithms of the different experiments in the rate laws. And then there's the way where you just use straight-on ratios. For example, what you can see is between experiment 1 and 3, one of the concentrations is constant. That means there's no effect on the rate of reaction from the initial concentration of NO. And I forgot to define this last time, I apologize. That 0 means that time equals 0, which is initially. So these are initial concentrations. That's what the little 0 means. Same thing for the hydrogen. But what we see is that from experiment 1 to 3, there's no change in concentration of NO, nitrogen monoxide. And there is a change in concentration, and the change in the concentration, it has doubled. And let me backtrack for a minute. Let me go back to this, write the general form of the rate law. Rate equals little k times the concentration of NO raised to some exponent we'll call A. Times the concentration of hydrogen raised to some exponent that we'll call B. Okay. And the point of this problem is to determine A and B, and then eventually determine K. All right, so now we come to this. We have 2 is the change in the concentration. Question, Esperanza?
You don't put a 0 on it? A little 0 for initial concentration?
You don't put a little 0 on it for these up here? So you don't, and that's because this will be the rate law really at any time. Or let's say this, it's always the rate law for the forward reaction. The complicating thing is after any time but time equals 0, it is possible to have reverse reaction. And so, but we're still trying to understand just the forward reaction at any time. So that's why there's no subscripts. Good question. Okay. Any other questions? Always good to get your bearings here as we start. All right. So, but what I'm going to put here is this concentration has doubled. That's where the 2 comes from. And the exponent on it is B. So I'm going to write 2 to the B. And that's like a shorthand for taking the ratio of the 2 experiments that we did last time. Remember, we would say experiment 3 divided by experiment 1, and we would get a 2 to the B factor. This part would cancel out because it's the same, whatever the value of A is. And I have identified a typo. Let me change this number to 0.0120. When I was typing out my notes, I missed that. But now from 0.06 to 0.012, there is a factor of 2. This is the shortcut method which says 2 to the B equals 2. Let's solve for B. B has to equal 1. That exponent is 1. Questions about that? Yeah?
So just to confirm, when the ratios are the same, like 1 to 1, then there's no exponent, like there's no A.
So we don't know what A is. When we're doing this, really ratioing experiment 3 to 1, whatever A is, the concentration of it is the same. So this is the same. So when we take the ratio, whatever this is, whatever A is, it still cancels out. Does that answer your question? Questions? Right, and so that's part of this, as you'll see, is finding, find the one thing that's changing, because that's the only thing that can be affecting the rate. Okay. Now, but here's the issue. The issue is that if I try and find one where this is constant, there is none. And so now we will have to use the ratio of logs method. Sorry, the ratio of experiments the long way with the ratio of logs, yes. And so here's what we're going to do. To determine A, the other exponent, we're going to take the ratio of experiment 2 divided by experiment 3. And we could have taken any ratio of experiments. It doesn't matter. Well, we couldn't have taken. Yeah, we could take any. Oh, we couldn't take 1 and 3. We could take 1 and 2 or 2 and 3. It doesn't matter. But this has to change. So what that looks like. So we're going to write rate equals k times and fill in a number. So for experiment 2, rate is 0.144. That's molarity per minute. Equals k times concentration of NO, 0.200 mole. Times concentration of hydrogen. Do the same thing for experiment 3. We have 0.0120. Equals little k times concentration Oh, and there's one other thing we know. We know B. So I'll just replace those by 1s. Now, this is, once we take the two, divide them. When you divide things that are equal by each other, you still get a true statement. We get our k's to cancel out. We get a number here, because we know the exponent. We get a number here, and the only thing we don't know in this is A. And now it's algebra. And we can do algebra. So practice the algebra. It is a good bet that there will be a problem that you need to do logarithms like this on your first exam. Not for sure. Certainly there's going to be an initial rate problem, almost for sure. And when you solve it, you will get A equals 3. So I'm going to skip the algebra, let you practice that at home. And this is an example where the exponent is 3. It says not only determine the rate law, but also the rate constant. That's a little k. Plug into the experiments, and you will find that little k, the rate constant, is 6.00 times 10 to the 9th, molarity to the minus 3, minutes to the minus 4.
Plug into the.
Good question. So where am I plugging into to find this? So this, I'm just solving that, right?
Right.
So I'm going to say you can plug into any of the experiments. I plugged into experiment 1. What I mean by that is you know the rate, you know all of these terms now, and you solve for k.
I got you.
Yeah. Any question about that? Yeah.
Why is similarity negative 3? Is it because it's...
Good question. Why is the molarity negative 3? If we come back to our rate law with 3 and 1 here, there's 4 molarities on this side. There's 1 molarity on the other side. And it's a good question, because one of the things I said last time was that K can have any units. Like they vary. They only depend on what the particular units are in the rate law. So, does that answer your question? Yeah. Other questions? This is probably one of the few times, so oftentimes on my exams, the units are worth 1 point, having them. This time, they're going to be worth a little bit more, because it's a little harder to find them. But they do matter. So. Cool. Any other questions about this problem? All right. A companion problem. Coincidentally, the companion problem is on the discussion this week. So we'll get to practice that for sure. So now we have the rate laws, meaning that if I give you a set of information in the table, you can find the rate laws, okay? And we moved from calculating rates to using those rates to calculate rate laws. Now we're going to go from rate laws to integrated rate laws. How many people in here have had some calculus? Raise your hand. How many of you know what integration is? Raise your hand. Okay. Now, there is no calculus requirement for this class, and there will be no knowledge of calculus may help you a tiny bit, though, because you're going to know the behind-the-scenes part of what we're doing. But otherwise, as you'll see, we don't do much good with this. So let's assume that the rate law is rate equals k times a. What order is this? What would we call that? Just a first order rate law. Good. Now, let's see. What we've done before for rate is we've done a calculation for the average reaction rate. And when we did that, it was just minus 1 over the coefficient times the change in concentration. Change in concentration should be delta concentration. Over change in time. Here, I'll remind you that little t is time and big T is temperature. And we will be using both this chapter for sure. Now, in this particular reaction, we're given that the coefficient is 1. So the coefficient term drops out. That makes this a little simpler. So we don't need that part. Now, this says rate equals k times a. This says rate equals minus delta concentration of A over delta T. I'm just going to set these two things equal to each other. Like so. And what this says is that the change in concentration with respect to per change in time is equal to some constant times the concentration. Anyway, so they get a little calculus-y there. Let me do one other thing. I'm going to rearrange. All I did was I took the A down to the bottom and moved the delta T up to the other side. I did say I was going to use cursive K, so let me be clear. This is still the rate constant we're talking about. Those are cursive lowercase k's. And I apologize, I'm going to rewrite it. Maybe a little cleaner. This is something that you can integrate, essentially, in calculus. Again, we don't do calculus in this class, so we're going to take this. We're going to follow the magic integration trail. Because we're not doing calculus. And we're just going to look at the results. And the results are something that you will have to know, and we're just going to have to memorize it, basically. Natural logarithm, that's ln. Of the concentration at some time t, concentration of A at some time t, divided by the concentration of A initially, or at t equals 0, equals minus kt. This is what's known as the integrated first order rate law. And you actually have to check the conversion equation sheets. I don't have them on the tip of my tongue right now exactly what's on there, but I bet that's on there. If it's not, let me know. We should talk. So, short answer, no to this. There we are. What does integration do? That's what we need to say next. What does integration do? If we plot concentration of A versus time, what we've seen from previous data is that because A is a reactant, some of A will react to A. And so we actually, in last lecture, calculated when there were points here some of these rates of reaction, average rates of reaction. So the slope of this curve is the reaction rate. The slope of this curve is the reaction rate. The equation for this line is the integrated rate law. The equation for this line is the integrated rate law. And that's what integration does. It takes the slope of a line, which is the reaction rate, and gives you the equation for the line. For those of you who have had calculus, does that sound familiar? Maybe. Well, maybe this is also a good use of calculus. But, and the true power of this is that now we can know the concentration at any time for A. For example, at t equals 0, it's just the initial concentration of A. Concentration of A at time equals 0, that's the initial concentration. And the true power of the integrated rate law, sure, it loses some of its wow factor with so many Marvel and DC Comics television shows now. But its superpower is it allows you to know the concentration of A at any time. And A is a reactant. It's very general form. If you're wondering why this affects your daily life, for example, if you take some sort of pharmaceutical and you want to know how much of that pharmaceutical is left in you after 2 hours, after 4 hours, after 6 hours, somebody has to do these kinetic studies to figure that out, to administer the correct dose. That's one example of how this could be useful in your so-called life. In your life. In your very, very, very good life. Okay. Anyway, any questions about this? All right. So then let's go on. And before we solve any problems, we will rearrange the first order integrated rate law. Bye-bye magic integration trail. And, well, let's say this. If we want to solve for the concentration of A at some time t, there's a better way to arrange this equation. What we're going to do is take the exponential of the whole thing. That's the EXP button on your calculator. Exponential function and natural log function cancel each other out. They're like 10 to the x and log x. So all we get when you take e to the ln of something is just that thing. These are cursive k's, little k's. And so e to the minus kt, this is another version of it. I find the most helpful version actually solves for the concentration at some time and puts the initial concentration on the other side. Like so. And so each of these versions, the version here, they are the same equation, just rearranged. And they're each useful for solving some problems. I believe they're each on the conversion equation sheet, but I'll have to check to make sure. Now what we're going to do is we're going to take the same equation, we're going to linearize it, and nothing up my sleeve. Is this linear right now? Not at all. One of my favorite things to do, linearize things, then make you plot them in Microsoft Excel. That's where we're going with this. Linearize in general means to make the equation fit the form of a line. That line is y equals mx plus b. Linearize, make this equation look like y equals mx plus b if we plot it correctly. If we plot it correctly, and we'll talk about what that means in a minute. Okay. Let's see. So what we're going to do, it's not that bad, I don't think. If you have a natural logarithm of two numbers that are divided, you can take them and separate them into the natural log of the top thing minus the natural log of the bottom thing. So all we did was just, I don't know what the math term is, distribute that. Is that the right term? Maybe. And then we don't do anything to the other side. And then lastly, I'm going to take this term with the natural logarithm of the concentration initially, add it to both sides to get it on the other side. Like so. Still nothing up my sleeve, and we're done. And then we write y equals mx plus b underneath, and we'll make some assignments. What that assignment is that if what's plotted on our y-axis is this, so plotting the natural logarithm of concentration, if we plot on the x-axis t, and so just to keep track of what's going on here, we've got our y part of our equation, we've got our x part of the equation, and now we can fill in what's left. M, the slope, if it's plotted in this way, the slope is the negative of the rate constant. And I cannot get that right, can I? The slope is the negative of the rate constant. Voila, instant rate constant. And the y-intercept is the natural logarithm of the concentration of A initially. And so what you will be tasked with doing is taking data for concentration versus time. You take the natural logarithm and plot it, and then replot it on the plot. Marissa? Good question. The question is, what's the benefit of linearizing the data? One is, you only have to do one experiment, and we're going to determine the rate law. We had to do multiple experiments before with that initial rates stuff. One experiment. Two is, when we determine the rate constant as the slope, we're actually averaging over all the points, so we'll get a better value. All right, well, if I'm not mistaken, we have a couple more things to do. The half-life. Half-life, the time in which half of the reactant is gone. So denoted by T subscript half. And basically, I think this would be a better way to say it. When we sub into our equation for concentration of A at some time, we're going to sub in half of the initial concentration. So for the first order integrated rate law, to solve for the half-life, I'm just going to put T to the half there. And when I'll write it again, instead of concentration of A at time T, I'm going to put half of the initial concentration. So I'm going to replace this, and I'm just going to write T to the half. There's a half right there. Sort of squeeze it in. Brilliant. Do I have the same thing in the numerator and denominator? Yes, those two things cancel, leaving me with ln of half. And then I just want, oh, yes. T to the half, the half-life is natural logarithm of 1/2 over k. Now the natural logarithm, draw my minus sign there, please keep that minus sign. Now the natural logarithm of half is negative 0.693. That's going to add another negative, so my answer will end up being positive. And I get an equation for the half-life, which equals 0.693 over k. This is specifically for a first-order integrated rate law. We've done first order everything to this point. Now let me show you all of the integrated rate laws. All of the rate laws, all of the integrated rate laws. We've done this. We've got the rate law, the integrated rate law, the units, the linear plot, the slope equals minus k, and the half-life equation. And we will not run you through all of them, but there's a similar process for 0th order. I like to think of Zeroff as a superhero of his or her own right. But that's 0th order. First order, second order. So I'm not going to do any more details about this. But here's what you have to know. Well, most of this data is on your conversion equation sheet. But when I give you a set of data, and I think I have a set of data coming up. Oh, I still have a couple slides left. But on the homework and in a couple slides, if I give you a set of data, you have to make 3 plots to determine what the order is. You have to make a plot of concentration versus time, natural log of concentration versus time, and 1 over concentration versus time. And we'll see that coming up. Here's a typical problem that you will find on the discussion and on homework number 1. The decomposition of that compound is a first order reaction. The rate constant for the reaction is 2.8 times 10 to the minus 3 inverse minutes at 600 Kelvin. If the initial concentration is 1.24 times 10 to the minus 3rd molarity, how long will it take for the concentration to drop to that value? How long? We're solving for time here, right? And when you're solving for time, this is the version of the integrated rate law that you want to use. When you're solving for final concentration, you want to use the version that has the exponential. But we're solving for time. And so I'm going to write out a version related to this. I like to stack up my logarithms. Plug in my terms. I have my rate constant k. I have my initial concentration. I have my concentration at some time t. I will plug all those in. Any questions about this set? Because at this point, it's just algebra. All you want to do is solve for t. I've sort of run out of space, so I'm going to put my answer up here just so you know, but it fits better down at the bottom. I get t equals 495. With some units that are coming, and the units are going to be in the problem statement. We see that the rate constant is in minutes to the -1. That means my answer has to be in minutes. We've seen minutes, we've seen seconds. You can do hours. That's mostly what we see, but you do want to check in with what your time units are. We're off on a strong Chem 401 unit cancellation binge, if you will. Look at my units canceling there. Whenever you have something within a natural logarithm, your units must cancel. Units cannot pass through natural logarithms. They can't pass, in that sense, they can't pass through logarithms either, or exponentials. And so you're left with knowing that the units on time have to be minutes.
So minutes to negative first power, what's that stand for on its own?
What? Say that again, please.
Minutes to negative first power, what's that supposed to?
Okay. Minutes to the -1 there, what that means is that it's really it's 1 over minutes. Now, if your question is what does that mean, I can tackle that next if you want. Sure. So let me think about what does the rate constant mean? Oh, it's a per time. Like, for example, it's a frequency is what it is. And it gets a little more complicated than that when you get to non-first order. First order, it's just a frequency.
Okay, so it's just per minute.
It's per minute, right.
Okay, sure.
Yeah. Right. What do they say? Always answer with the least amount of words possible that still makes sense. There's more to say, but if that makes sense. Okay, I'm going to say it anyway. So, how many times do you come to this class per week? Twice per week. That's a frequency as well. It just means how often does something happen. In this particular rate, it means how often does the reaction happen. But yeah, it's a frequency per minute. Cool. Thank you. Good question. Any other questions? I will tell you, by the way, that when I did frequencies for Gen Chem and then physical chemistry, they bedeviled me. I could not, for the longest time, understand what a frequency was. Still not 100% sure when it comes to electron frequencies, but anyway, it's an important point to clarify and easy to get stuff on. Companion problem solved already on the Chem 401 website. But like always, companion problems, the more you see something in lecture, homework, and discussion, the more likely you are to see it. At some point, it becomes like everything's possible. Here's a lovely data set for a reaction. It says plot the following data in Microsoft Excel to determine the rate law and the rate constant given the following data. This data is for this reaction. We have time versus concentration. And this is what I mean by you have to plot it. You have to plot it 3 different ways. Here we have, and I apologize if this is a little small, this is concentration versus time. This is what's called the 0th order plot. Natural logarithm versus of concentration versus time. That's the 1st order plot. And the 2nd order plot already says 2nd order plot on it. And it is poorly labeled, so let me label it. 1 over concentration versus time. And in which of these plots does the line go through the points the best? The 1st order plot, look at this. All the points fall on the line here, not so much. Here, not so much. That is what you need to do to determine what the rate law is for this data. You make 3 plots. Whichever one has the highest r² value, and if you were in my Chem 400, we did talk about r². What we said was that r² being closer to 1 means that the points fall closer to being on the line. The points are more well fit by the line. And here's a use for the number to tell us something cool and useful. So, on the homework, when you get a set of data and it says, plot the data in Microsoft Excel to determine the rate law, done. And we will do this in discussion. I think it's actually not this week. It's on Kinetics 2, which will be next week. And we'll bring in computers to do it. Now, all right, so check. Based on those plots, it's 1st order. Okay, and then rate constant. How do we find the rate constant from that plot? You remember what we said? Slope equals minus k. Now, let me be clear. This equation only has 1 rate law. We are doing 3 plots. 2 of them say this is not the right rate law. Those are the ones that are not linear. Another aspect of this is you have to have a wide range of data. The wider the range of data, the more you can tell that this is banana-shaped data and not a line. You might imagine if we tried to pass a line just through those first 3 points, they all might look linear. So this method has its limits. Any questions about that? If not, we have a companion problem for this one as well. Gives you a chance to plot, and I have the plots that I made up on the Chem 401 website as well. Plotting things, very useful in this class. step by step. Start with calculating reaction rates, then go to determining rate laws. Now we know integrated rate laws. The next thing we need to do is start talking about how these reactions are actually happening. That's the subject of reaction mechanisms. Reaction mechanisms I think it's a bit wordy here. The sequence of molecular events or elementary reaction steps that defines the pathway from reactants to products. A few terms here. An elementary reaction step is a molecular event, a single step in a reaction mechanism. You can relate coefficients to exponents in the rate law for elementary reaction steps. We'll have the overall reaction, which still describes the reaction stoichiometry, similar to Chem 400. And it's also the sum of the elementary reaction steps. So our process will be to hypothesize a reaction mechanism. We will know the rate law, and the rate law of the mechanism must match the experimentally determined rate law. And the steps must add up to the overall reaction. All right, notes. Always show all species in a reaction mechanism. So NO2 plus NO2 as opposed to using a 2 coefficient. The reason we're going to do that is because, so we can act it out, of course. So if these are the two reactants, your thought process is NO2, NO2, actually colliding. That's a molecular event, an actual collision occurring. That's where we're going with this. All right, so that's very wordy. Let's see what we mean in practice. An overall reaction is given here, and we are told the rate law. Because we've already done all that other stuff to determine what the rate law is. Hypothesize a reaction mechanism. Now, from the previous slide, which is still there, good news, we can see that whatever we're going to hypothesize must fit two things. One, it must agree with this, and the steps have to add up to this. And beyond that, this is an opportunity to be a bit creative. Now, I'm going to hypothesize some things, and I'm not going to tell you how we know when it agrees with this part yet. That'll be in a couple slides. Well, let's just see what's going on here. So we're going to hypothesize the following reaction mechanism. Step 1. O3, the ozone molecule, and we will leave phases out of this. And we'll just be a molecule. That's a K sub 1. And it is the rate constant for step number 1. And that's an arrow that I have. O2 plus O. And for elementary reaction steps, you can relate coefficients to exponents. What that means is, if there's a coefficient of 1 right here, or well, they'll all be 1, but say there's not 2 of them, there's just 1. It's just, so all I did is I took the rate constant for this step, and I multiply it times the molecule here. Dylan?
Do states matter?
Do states matter? The short answer is, of course they matter. This next level of understanding is that for reaction kinetics, really most of what is known started in the gas phase. So we can imagine that ozone and most of the things that we're going to be looking at are in the gas phase. And that's the sort of the Chem 401 level of understanding is when we think of, so what is the molecular event? Here's ozone, and it breaks into 2 pieces. That is what we are hypothesizing right now. So there's no collision yet. Let's actually get a little more detail, because when this process occurs, there is actually a collision. Oh, no, that's. It's actually UV light that does this, and that's what breaks up ozone in the upper atmosphere, or somewhere up there. I'm not sure if upper atmosphere, somewhere above us. There is actually a collision, but the UV light doesn't show up as a something with mass interaction. But anyway, so it's really. All right, so that is the molecular event. Dylan, what was your question?
Oh, it was just if states matter.
Oh, if states matter. Yes, well. Sorry, I went off on a tangent there. But so eventually, and really the interesting stuff for biologists, which I know some of you are, is thinking about enzymes and reactions in the body. And of course, those are not in the gas phase. And they get more complicated because instead of thinking of a collision between two things that are isolated, meaning there's nothing else around them, meaning they're in the gas phase, then we have to start thinking about, let's say, something in the aqueous phase. Something in the aqueous phase, like an ion, could have a hydration shell around it, and so could act isolated in some ways. Anyway, it gets more complicated, but for us, you will see that almost everything we do is in the gas phase, even if we don't mention it. Other questions? Yeah?
Or can you explain again what your expression by putting K1 over the reaction?
Yes. This K, so I'm going to have a step 2. It's going to have a K2. It's just to separate these two.
So we're separating out, there's going to be a different K value for each step of this overall reaction.
Each step will have its own rate. Yes. And eventually where we're going to determine how this matches the experimentally determined rate law is we're going to have to talk about the relative rates of the steps. We're not quite ready yet. Yeah, but that's what. Okay. Any other questions? All right. And just to be clear, this step 1 is an elementary reaction step. We don't usually write the word elementary, but that term means this literally happens in our hypothesis. As opposed to the overall reaction, which allows us to do stoichiometry and says nothing about how it happens. It just says we start with these, we end with that, and we would rather not speak of how it happens. Step 2, well, the key to step 2 is doing what you have to do, get her done, to make it match the overall reaction. So I see that I've made an O2, thumbs up. I see that I've made an O in my hypothesis that does not show up. So the next thing I do is I write it in step 2. I'm going to put it with an O3. That's rate constant for step 2. And literally, I have my O that I created in step 1 colliding with an O3. Whatever happens, it makes 2 O2s in the end. So there's some bond breaking and some bond making there. It's true. And rate, little k2 times concentration of O times concentration of O3. Like so. And what helps me stay organized and all this stuff is I always add them up. I always prove that the steps add up to the overall reaction. I have my 2 ozones. I have my oxygen atom that I created in step 1 canceling out in step 2. Let me define what this is. There's a term for this. This is a reaction intermediate. And a reaction intermediate, sorry about this, is literally in the intermediate parts of the reaction. You'll identify it though because reaction intermediates show up first as a product and get canceled out of the overall reaction. So working definition shows up first as a product and then gets canceled out. Angel?
That's the case. Does that mean K1?
Question, if that's the case, does that mean that K1 equals K2? The short answer is no. The longer answer comes in a slide or two. But you're right, there's some things we're going to do with those coming up. Yeah. Marissa? Great question. How did I know to add this? And the short answer is I didn't. Like, there are multiple possible hypotheses that I could have made. I could have made O3 plus O3 goes to O6. And O6 spontaneously breaks down into 3 O2s. Right? O2 plus O2. Like, that would be a two-step mechanism. That would be, I would say, a little less likely, but I know that only because I know that O6 is completely unstable, right? But it's a valid hypothesis. And that's where I want to sort of go to is these are hypotheses. And if I hypothesize, and we're not quite ready to say this is a good hypothesis yet, but if I come and I say, oh, this does match for whatever reason, and this is my hypothesis, the next step is to go use some sort of chemistry instrumentation to find evidence of O. And then if we find evidence of O, and I could talk about that as well, but if you find evidence of O, then you'd say, I have good evidence that this is how it happens, and now, yeah, so it goes from there. Like, you hypothesize, it's scientific method stuff. Then you go find evidence. If you don't find evidence, you better come back and make a different hypothesis. Does that answer your question? Yeah. Logan?
We know from the rate law that was given rate equals A from the concentration of O3.
Yes.
That we have a zero order reaction. Right?
This is
The
first order.
reaction.
Yes.
So we didn't need to add any coefficients on our rate equals K1 times concentration of O3. But how do we know for the rate equals K2 times concentration O times concentration O3 that there's no coefficient? How do you know the order of that second step?
Oh, how do we know how this relates to this reaction?
Well, so it seems like we're building rate laws here,
We are building rate laws.
which normally have coefficients next to the concentrations.
Do you mean exponents?
Sorry, exponents, yeah.
Yeah.
Exponents, sorry.
Okay.
So how do we know that we don't need exponents for?
Perfect question. The question is, how do we know we don't need exponents, like little a and little b here, right? Okay, so according to this, and this is the definition of the process, you can relate coefficients, all the coefficients are ones here, to exponents. So, and that's an assumption, but it's a good assumption, right? And maybe it comes back to why we can't use coefficients here. This is only the stoichiometry, right? This does not say how on a molecular level this reaction occurs. And that's what we're getting into now. Yeah. And that's a fine point. For reaction mechanisms, coefficients, right, which I told you to write each out individually, but coefficients, are exponents. Wouldn't it be nice if this was the step that was important? All right, but I was defining reaction intermediate. The reaction intermediate appears first as a product. And cancels out of overall reaction. Now, and the other way of looking at it is that the O does not appear at the very beginning. It does not appear at the very end. It only appears in the intermediate parts of the reaction mechanism. And I'm being very careful to explain this because we will have something that does appear here and does appear here and does cancel out. And those will be catalysts. No need to write about that yet, but that's why I'm being very careful to tell you where this appears first as a product. Finally, let me write my overall reaction. It does add up. And you can write them all, for overall reactions, you can write them all out. Or, since they're only showing stoichiometry, you can put them all together. Either way is fine with me. All right. Yeah, so that was our first mechanism. I believe we'll be coming back to that one, but let's do another one. Here, overall reaction, NO2 plus CO, nitrogen dioxide plus carbon monoxide, goes to nitrogen monoxide plus carbon dioxide. All of these are gas phase species. Rate equals K, well, it's a second order rate law. Give myself a little more space. Hypothesize reaction mechanism. One step, start simple. There are many possible hypotheses. Let's start with step one. NO2 plus CO. In this process, NO2 is colliding with CO and making these two. And because it's a step in a reaction mechanism, we can write a rate law from it. It goes like this. Rate equals K1 times concentration of NO2 times concentration of CO. Does that match our overall reaction? Does it match this? It does. Does it match this? No. So it's a bad hypothesis, but I will encourage you to always start simple. The simplest one is just to assume that the reaction goes to the two reactants collide with each other, make products, done. So, done. Perhaps we should have called it step only. We probably called it step one. Done. Okay, notes. Reaction mechanism agrees with overall reaction, thumbs up. Reaction mechanism agrees with overall reaction. Well, we'll give it a check. That's one of the two criteria. Next thing, reaction rate law, or rate law for step one does not agree with experimental rate law. Thumbs down. Rate law for step one does not agree with experimentally determined rate law. Sad face for this reaction mechanism. But we're all about process in Chem 401, I always say start simple. Now let's get more complicated. I think we get more complicated, yes, on the next sheet. Same example from previous page, same reaction. Now we're going to do the two-step. Incidentally, when I go clubbing, I do the two-step.
That was a dad joke. That was a bad dad joke.
That was terrible, wasn't it? All right. Now, let me ask you, what would be a good step one to hypothesize? Knowing the experimentally determined rate. Yeah. Say that again. Oxygen separating from NO2. So we know we want to make that, right? Okay. Let's take a step back. Reaction mechanisms, so you're right, reaction mechanisms are collisions. What do we want to have collide if we wanted to match this? NO2 and NO2, right? If we can't start simple, let's at least start, well, now let's say this. We started simply for matching the overall. Now let's match the rate law and see what happens. Yeah. Step one. Okay. And we do whatever happens, we want to make NO. And at this point, you could hypothesize that you make NO3. You could hypothesize that you make another NO and another O, too. But let's keep it simple. Let's just make one more thing. Nitrogen trioxide. Rate equals K1 times concentration of NO2 squared. Question, Hannah, and then Dylan.
So I thought the exponent 2 is just the reaction order, like for our rate, the rate equals. So then how? I know you're saying you want it to match the experimental rate.
Mm-hmm.
What do you mean by that? What do you mean by match the experimental rate?
Ah.
I don't really get how you're connecting that.
Do these look similar? If not the same, except for the fact that there's a 1 subscript in one of them?
Yeah, but I guess I'm just confused because you're dealing with rate, the rate order and then like 2 NO2 molecules. I don't know if I feel like I can't explain what I'm trying to ask, but
I mean, that's another way of writing it, right? So I had 2 of these. I could write it like this, and then I abbreviated it. But be clear, I wrote this step to agree with that.
okay.
Is that
Yeah, I guess like when I look at it, I don't want to think of it as NO2 squared.
understood?
Like,
Does that help though?
but, yeah, I didn't know that. I guess, is that then one of the, where it says the exponents and the coefficients?
Can be are coefficients.
Are coefficients. Okay.
Dylan?
Okay, so if we had like a more complicated example even than this, and like say we had to hypothesize creating other things,
Mhm.
like would we have to draw Lewis structures if those things were like super complicated to see if they even exist?
It's a great question. If you hypothesize something exotic, right? My favorite thing to hypothesize are unicorns, but they don't show up in these personally. But yeah, so okay, we're going to hypothesize things that will be a little exotic, right? We're not used to seeing an O. I know you've seen NO2. I know you've seen NO. I don't know if you've ever seen NO3. So it's already a little exotic. Yes, we let's see. Odd number of valence electrons. Be tough to draw something with octets on it. But yes, you could be asked to do that. That's a great idea.
Thanks.
No, I already had that idea. But let's say this. So when you hypothesize something, you want to think about how realistic it is. Like if you were really doing this, you would go draw the Lewis structure, or you would go and calculate atom distances and bond strengths using a computer, right? Or you would do it experimentally. You would go say, well, NO3, I think this is the Lewis structure. It should have a bond that absorbs energy in the UV or the infrared. And so yes, there are logical next steps to take that are beyond Chemistry 401. Does that answer your question? Marissa? Yes. We canceled out the O because it was an intermediate. How do we know it's intermediate? Because we saw it on the product side and then we saw it on the reactant side. That's really why we canceled it out. Hang tight, we're getting there. We're going to see another intermediate here, and then we're going to talk about what to do with intermediates, okay? But the short answer is intermediates cannot appear in our rate laws because we're hypothesizing that they exist. So we will deal with those. Yeah. Question, why can we relate coefficients to exponents in elementary reaction steps? Good question, because these things are literally happening in our hypothesis. So if two things actually collide, we would expect the concentrations of each of them, or that's the same thing in this case, we would expect the concentration to influence how it happens. So, like, as we'll see, in this step, if you double the concentration of NO2, right, it already tells you that the rate squared, or that will make the rate go up by a factor of 4. Right? But that because things involved in the actual reaction steps should impact the rate. It's sort of I think I see where you're going. It's a hypothesis as well that it will be direct like we are assuming, but it turns out it's a good hypothesis. Things that are actually colliding, if you get more, you will have more collisions, which means more reaction. Maybe that's, yeah, that might be what I was going for there. Does that answer your question?
I just can't really understand it mathematically with software anyway, so.
I would say, so we're like in season 3 of Game of Thrones, where you think you know who's gonna live and die, but you're not sure, and then they kill the main character, and you're like, oh. So some of where we're going is clear, but some of it is not yet. But we're like, so hang on to those questions, keep asking them, but some of them I'm going to say, hang tight, right? I just said to Marissa, hang tight, we're getting there. How do we know? And some of them I'll be able to answer, so keep asking. But that's as much as I can say now is if there's more, if NO2 is in the reaction mechanism and right, these collisions are occurring, you have more NO2, there will be more reactions, which means faster rate. And if 2 of them are involved, then what we're suggesting is it should be the square of that. Because it's influencing both halves of the collision. Anyway, but yeah, good question. Cliffhanger. We'll stop there. I'll tell you what, finish up the reaction mechanism, and I will put the finished reaction mechanism on the board next time, and that's where we'll start. See if you can do it. Where did I get NO3? Let's see. It was in my pocket.
Yeah,
That's right.
there's like 6, 7 main characters.
I'll tell you what. Do you want me to ruin it some more?
No one's safe in Game of Thrones.
Hi, folks. So we have 10 minutes for those of you who have discussion next. Hang out. Let's take a break.